Hello, and thank you for attending my presentation. My name is Nathan Lhote, and I'm going to talk to you about Pebble minimization for polyregular functions. So I'm going to tell you what polyregular functions are, but before, let me talk about regular functions. So regular functions can be defined by several different models. Here I have a two-way automaton, so that can move forward or backward. And this one in particular reads a word and here loops, and when it reads a letter it copies it. So the red labels are for the input and the blue for the output. So it copies the word and moves forward, and when it reaches this end marker it starts moving backwards, and then it copies the word again, but moving backward. So the function realized by this automaton is the function that takes some input word and produces this same word concatenated with its reverse. A different way to define regular functions is through Mso transactions. So an Mso transaction is given by a set of Mso formulas, here on the right. And the idea is that you will define an output structure here based on a number of copies of this input structure. So you have several formulas, and I only gave a few here. So here this formula phi A1 of x says that the first copy of the position x should be labeled by A when the input structure is labeled by A on position x. So this position should be labeled A, and this one should be labeled A as well. And then you could imagine the same formula but for copy number 2. Then this formula says that this edge will be present between the position x1 and y1 when there's already an edge between x and y. So it means that this edge comes from this edge. And you can similarly define these reverse edges. And then the final formula tells you when you have an edge between a position of the first copy and the second copy. And that's only when x and y are the last positions. So here you have this edge. Okay, so that's two ways to define regular functions, and it was shown by Engelfried and Hugeboom that these two models were equivalent. So they're called regular functions because they have several different characterizations, something like 5 or even more and counting. And we have this strong automata and logic equivalence that's very useful. And they have many closure properties, including composition, that are very nice and natural. So how to go beyond regular functions, but still preserve some regularity? So the automaton model we'll be considering is the one of Pebble automata, which was first considered by Globerman and Harel. So in a regular finite automaton, even a two-way automaton, the length of a run is always linear in the input word. And for Pebble automata, the length of the run will be polynomial. So what is a Pebble automaton? So you have your input here on a tape, and you have several reading heads that follow a stack discipline. This means that only the first reading head, here, the top of the stack, can move. The other ones cannot be moved or replaced. And how does the transition function work? So you have a current internal state, then you read some letter. So here the letter of the active head is B, and then the active head is aware of which of the other heads are on this current position. Then you produce a new state. You can move the active head to the left or to the right, or you can pop the active head. So you remove this head, and now 3 becomes the active head. Or you can use push and add an additional reading head that will become the new active head. But there's a limit of k heads in total. And then you can produce some output, and this we will call a Pebble Transducer as opposed to automaton. So that's how it works. Let's see it on an example. So here we will be realizing the suffix function, so the function that takes some input word and produces the list of all its suffixes. Here I have the transition table. And so let's start. We start with only one reading head and on this left-hand marker. And we are in state Q0, and we know from the table that in state Q0, whatever we read, we go to Q1, we move to the right, and we don't output anything. Okay, so we move to Q1 and to the right. And then in Q1, we go to Q2 and we push a new head. So that's what we do. And from Q2, you can see these two transitions. From Q2, we will copy all the positions and move to the right. So copy the whole input until we reach the end marker, and then we pop this head and move back to Q0. So let's do that. We copy the whole word, move to the end marker, pop the head, move back to Q0, and I jumped a transition. After Q0, we move to the right and to Q1. And then we do it again. So we push Q2, we push a new head and move to state Q2. We copy the whole input. And once we're done, we pop the new head, introduce some separating symbol, and go back to Q0. Then we move once to the right, push a new head, copy the word, and pop the new head. And we continue until we reach this end marker, and then we accept. So here we have indeed realized this suffix function that copies all the suffixes of some input. So this Pebble Transducer, they realize functions that have been coined polyregular functions by Mikołaj Bojączek 2 years ago. And he shows in his paper that they are characterized by many different models. So the Pebble transducers, which were first introduced by Milosu, Chu, and Vianu. Another very interesting model is called 4 transducers. So it's an imperative programming language with 4 loops that can iterate through some input word. So here you have the first for loop that goes from the first position to the last position of some input. Then you have a second nested for loop. Here you go through all of the possible letters, but that's just syntactic sugar because the alphabet is finite. And then you have if statements. So you say that if the label of y is sigma and x is smaller than y, then you output sigma. And here, at the end of the inner loop, you output some separating symbol. So this function realized by this for program is the same suffix function that we saw before. Another model that was considered in this paper of 2019 is the Mso Interpretations. So an Mso interpretation is very similar to the Mso transduction that we talked about previously. But this time, the universe of the output structure is not given by a certain number of copies of the input, but by tuples. So here it's a two-dimensional Mso interpretation. So the universe of the output will be pairs of positions such that x is larger than y. Then we say that two positions in the universe are related by the less than relation, basically if they are in lexicographic order. And then the label of some position in the output is just the label of the y coordinate. So if you have some input ABC, the output will look like this. So it's pairs of positions that constitute the universe of the output, but we want x to be larger than y, so these are not part of the universe. Then the label is inherited by the y coordinate. And then the order is the lexicographic order. Okay, so that was Mso Interpretations. Then there's the composition of prime functions, so a small set of functions such that any polyregular function can be obtained by just composing them. So you take as a basis the sequential functions, which can be even further decomposed through the Krohn-Rhodes theorem. Then there's this iterated reverse function that takes some input, and for every block between two separators just reverses. Then there's the square function, which is the first function that has polynomial size increase, which takes a word and makes one copy for each position of the word, and then underlines the position corresponding to the number of the copy. And finally, there's the list functions, which is a very small functional programming language, where you have lists and lists of pairs and pairs of pairs and so on, and then you can compose the functions and use different operations on the functions. Okay, so that's the polyregular functions. Now let's talk about what we are really interested in. So Pebble minimization for these Pebble transducers. Okay, so we want to study Pebble minimization, and there are several reasons for it, and one of them is that if you have, let's say, 4 pebbles, then the length of the run will be bounded by the size of the input to the 4th power. So having fewer pebbles is always good. So for instance, we could be interested in this problem. So we have a polyregular function, and we would like to know if it's regular. In other terms, we would like to know if this function can be realized by a Pebble transducer with only one pebble. Then there's the more general question of, can we minimize the number of pebbles? And then we would also like to understand if there's a connection between the dimension of Mso interpretations and the number of pebbles used to realize a transduction. So we already know that Mso interpretations can easily express, so with k dimensions, can easily express the runs of k Pebble transducers, but it's really not clear how to transform a k-dimensional interpretation into a k-Pebble transducer. And it's not clear even if it's possible. So let's start with a very simple case, extremely simple. It's the case of regular functions. So a regular function, which can be seen, as I said, as the one Pebble transducer, the length of its run is at most linear, So we know that the functions realized, the functions are at most linear. But we would like to know when is a regular function bounded. So we can see easily that a regular function is not bounded if we can find in the run some kind of loop that produces something. So loop would look like this. So we have a run of a two-way automaton or two-way transducer. And at some point we have some sequence of states. That repeats in the run. And we have some non-empty output, for instance, ABC, at some point. So here it's easily seen that if we have such a loop that produces something, then we can pump this loop and obtain linear size output. But conversely, if we don't have any producing loop, then that means that all the loops are non-producing and we can collapse them. And once we have collapsed all of the loops, then the input has bounded size, and we know that the function is bounded. So we have an equivalence between being bounded and not having any producing loop. So we have this dichotomy, either the function is bounded or it's linear, exactly linear. Okay, now let's move to the two-pebble transducer case to see how we can generalize this idea. So we can see a two-pebble transducer as a one-pebble transducer, which we call T1, where every time we want to push a new pebble, we replace this by a special output symbol which says this C2, which says I'm calling for the second pebble. Then we can study this transducer T1, and if this transducer T1 is bounded with respect to this special symbol, then we know that the function has to be linear, because we make only a bounded number of calls to the second pebble, which can only realize a linear function, and T1, the other outputs of T1 also are linear in size. So if T1 is bounded, then the whole function is linear. Okay, what if T1 is not bounded? Then what can we say? Well, the main idea is to modify T1 slightly so that it only outputs C2 when it's absolutely necessary. What do I mean by absolutely necessary? We look at the word, the current configuration when we want to output C2, and we can ask through some regular look around if there is a producing loop for the second pebble. So we will call the second pebble, and we ask if there is a producing loop for this second pebble. If there is none, that means that the output from this second pebble is bounded, and hence we don't need to call the second pebble, we can just produce this bounded output. So that's what I mean by absolutely necessary. So we modify this T1 to T1 prime, and we only make the calls when they are absolutely necessary. And the result we obtain is that we only need to check if this T1 prime is bounded with respect to C2. Okay, now let's move to the general case. It's the same idea as above. So we see a K+1 pebble transducer as a one Pebble transducer that can make calls to K Pebble transducer as a subroutine. So we use this look around and the induction hypothesis to remove these useless calls. So a useless call would be a call where we don't need really the K pebbles. So that would be that the growth of this transducer Tk is not in n to the k. If it's not in n to the k through the induction hypothesis, we could replace this call to a K Pebble transducer by a K minus 1 Pebble transducer. So we check if this T1 prime, where we removed all the useless call, is linear or not. If it's linear, then we know that the function will be in total in n to the k plus 1 because we make a linear number of calls, and these calls we know that they are not useless calls, meaning that they produce some n to the k sized output. So since the function has this growth, it cannot be realized with only k pebbles. If the number of calls is bounded, then the function can be done with only k pebbles because we only need to remember how many calls we've made so far, and this can be done with finite memory. So the first pebble is superfluous. So what are the main results to sum up? So first we have this very nice characterization that a polyregular function can be defined by a transducer with k pebbles if and only if its growth is in n to the k, with n being the input size. Then we have an even stronger result, which is this minimization, which says that given a polyregular function, we can minimize the number of pebbles that we need. In particular, we can decide if a function can be realized with one pebble, that is, if it's regular. And finally, through the 2019 paper, we know that Mso interpretations can be realized by Pebble transducers. But through this result, we know since k-dimensional Mso interpretations have growth in n to the k, we know that actually they can be done with only k pebbles, and we have this nice correspondence. So what are the possible ways to extend this work? So first, it would be interesting to study the growth for the other models that were introduced by Bojanček. For example, the 4 programs. So we could think that the nesting depth of 4 programs gives us the same hierarchy of functions. However, already for regular functions, we may need arbitrary nesting of 4 loops. So these define a whole other hierarchy, and it would be interesting to understand it better. Then for polyregular functions, there are many existing models, but one that is lacking is this model of register automata. And then there's this question of equivalence, which is wide open. We don't know if one can decide the equivalence of 2 polyregular functions. Thank you for your attention.